To do a multi-step calculation using proper significant figures, first do the calculation without rounding. For example, we can add 1.213 plus 2.5, then divide by 6.75, and come out with 0.550074. After doing the calculation without rounding, go through it again, but this time pay attention to proper significant figures. The first step in this problem is an addition, which gets rounded based on digits after the decimal. Our second number, 2.5, has one digit after the decimal. Therefore, we round the answer in our numerator to one digit after the decimal, making it 3.7. Once we have rounded based on our addition rule, we determine the number of significant figures in that answer, so that when we do the division, we can have proper significant figures. 3.7 has 2 sig figs, and 6.75 has 3 sig figs. So our answer gets rounded to 2 significant figures. At this point, we reference our original unrounded calculation, and we round that number to 2 significant figures. 0.550074 rounded to 2 sig figs is 0.55. An example of a multi-step calculation is one like we do in the lab. We are using Archimedes' principle to determine density of a metal bar. We are using the equation density equals mass divided by volume. Mass in this example is 69.658 grams. Volume is the difference between final volume, VF, which is 22.4, and initial volume, VI, which is 13.5. We first go through the calculations without rounding and come out with 7.8267 grams per cubic centimeter. We go through the calculation again, paying attention to significant figures. The subtraction step is based on digits after the decimal. Since 22.4 and 13.5 both have one digit after the decimal, we keep one digit after the decimal in our denominator, and the number is 8.9 milliliters. Since 1 milliliter is equal to 1 cubic centimeter, we can change the units to cubic centimeters. We want to do this because we are trying to express the mass of the metal bar, which is solid, rather than the mass of the water, which is liquid. Then we do the division step, which is based on total significant figures. The top number has 5 sig figs, the bottom has 2. So we keep 2 sig figs in our final answer. When we round 7.8267 to 2 sig figs, we come out with 7.8 grams per cubic centimeter. After carrying out the operation, parentheses 13.7 plus 0.027, parentheses, divided by 8.221, how many significant figures are appropriate to show in the result? Is it A, 1, B, 2, C, 3, D, 4, or E, 5? The correct answer is C, 3. The first step is an addition step, so we are going by digits after the decimal. Because of the first number, we are limited to one digit after the decimal, giving us 13.7 as the result of the addition step. 13.7 has 3 significant figures, which is less than 8.221 has, so the answer will have 3 significant figures. If this problem had asked us for the actual answer, we would need to do the problem without rounding any of the steps, and then round our final answer to 3 significant figures. As we make measurements in the lab, we are interested in finding the accuracy and precision of our measurements. The accuracy is how close your value is to the true or accepted value. To use a bullseye analogy, something with high accuracy would hit very close to the center of the bullseye. The way we would determine accuracy in the lab is with percent error. Precision, on the other hand, is how close your measurements are to one another. In other words, how repeatable is your experiment? Do you get the same value every time? That doesn't mean your value is necessarily correct, just that you are consistent. Figure B shows a bullseye in which the holes are precise but not accurate. They hit in roughly the same place every time, but it was not the center of the bullseye. Precision is determined in the lab using standard deviation. The formula for standard deviation is a way to compare each trial to the average, which is a way to compare the trials to one another. Figure C shows something that is neither precise nor accurate. The holes are not in the center and not near each other. In the lab, if you are doing an experiment that has never been done before, you may not have a true value to compare your results to. Therefore, you could not measure accuracy, but could only measure precision. The more repeatable your experiment, the more likely it is that you have found the true value.